I wanted to talk to you a little bit today about some study I'd done about Eero Saarinen and his work with his structural engineering consultants on three different shell projects. I call this Formative Experiences, Saarinen Shells, and the Evolutionary Impact of Construction Challenges. The era for this thing is in, of course, the middle of the 20th century, and you're going to see the interesting parts just about Saarinen's attitude as a designer, a collaborator, and even then the role of structural shells, long-spanning concrete structural shells, and whether these are strictly engineering based in terms of their form and expression, whether these have a different aesthetic architectural agenda that can be separated from those considerations, and of course the impact of actually having to build such a unique type of structure. So here's the story. Eero Saarinen Associates, you can see pictured up above there. There's Eero Saarinen and Kevin Roche. Worked on three different shell projects within just a little bit more than a decade. The first one, Kresge Auditorium, from 51 to 55 on MIT's campus. TWA, the TWA Airport at Idlewild, from 56 to 62. And of course then the Dulles Airport Terminal from 58 to 63. And Dulles was the last project that Saarinen worked on before he had died in 61. All three projects are basically continuous throughout a decade. The other thing that's important to note is there was Ammann and Whitney engineers were the engineers for all three projects. I set out on this construction history research project trying to answer one question. Why do these buildings look so different? If they're done by the exact same design team, what happened from 51 to 58 that changed the way that these projects were conceived, designed, documented? What I found was what happened is that the relationship evolved. Kresge didn't start off real well. What you're looking at here is pictures of Eero Saarinen looking at the shell right after the scaffolding had been removed. Now, this was a very famous project before it was even built. It was going to be the U.S.'s longest free-spanning concrete shell project at 160 feet. Now, there was other shell projects in Europe at the time that were longer, but this was an amazing feat in the U.S., and Saarinen was an up-and-coming budding star architect. So he was interviewed for Harper's Bazaar magazine, and they took pictures of him at Kresge. Unbeknownst to the photographer, but known to Saarinen at the time, was the building had started to sag. These concrete arches that he's standing on and looking up actually were in a 6-week-long phase of sagging that threatened the viability of the structure. They are sagged 5 inches in the middle, which is 3 times as much as they were designed to sag. So what happened? What was going on? So the story about this project was Saarinen had originally designed other concrete shells that actually matched forms that other forms that were known to work as concrete shells. You can't just randomly make a shape and say, there, it's a structural shell. There's certain rules that come with a double curved surface. He was kind of obsessed about shells with the GM Tech Center project. And you can see that he also thought of this contextually as not only something for a university interested in, as he says here, progressive technology, but MIT's campus also has several hemispherical domes around campus. So why not do a hemispherical dome like he did at the GM Tech Center? Well, the problem, and you can see it a little bit in the triangular drawing here, is this is a 1/8 of a sphere that rests on 3 points. He chose that shape because it actually matches the fan shape of an auditorium. And then in the section you can see the curvature of the inside. He was obsessed with trying to make sure that the acoustics would also be right. So plan shape, the triangular form sort of worked. Hemispherical, sectionally it worked. And then the last thing is he wanted it to seem like it was floating. So in the bottom you can see here, by having it only rest on 3 points, he wanted it to seem like it was, of course, progressive technology. So proportionally, it was only, the thickness of this thing was only about 3.5 inches, which is less thickness than an eggshell is. In their office, they had drawn several schemes, and this particular scheme was called the Vulgar Freak by his group. They had built models and drawings because it didn't match any structural form. Now, Eero Saarinen said this is the one that matches both for plan and acoustics and the aesthetics of being floating, and had a grapefruit peel and actually used a grapefruit peel. Even though it sounds like it's a myth, it actually happened. And he showed that it really could float on those three parts. And so he said, it's the loved one. This is the one we're going to do. It's no longer the vulgar freak. And folks, this is when he hired Ammann and Whitney. So he hired Ammann and Whitney, who was the nation's leading structural engineer at the time for concrete shells, but they already had a form set. Normally, a structural engineer would then work with the architect to find an ideal form, and they'd both work together. But Ammann and Whitney was picked to sort of make it work. So what happened was they started to document the geometry of it, not the construction, not even how it works structurally. So Saarinen said it was structurally appropriate, but it wasn't. It was highly speculative design. There was no relevant example that Ammann and Whitney could go off of, or even Saarinen's office, for how to do such a thing. So they invented their own way of documenting it. Here's the plan, here's the section. What they did, though, is they documented it in a way that helped with how they would draw an orthographic projection. They set these coordinate points of radii, A, B, C, etc., and then distances in the both x and y axis, so that if you looked at both plan and section, you'd be able to identify where this x and y point were, and then theoretically you could redraw that. Doesn't help you build it. And then the absolute crazy part to me is the specifications for this in the concrete section. They essentially had a standard spec section for concrete. It didn't have any specific language about pouring concrete shells, and normally this is its own section with very specific requirements. Look what it said here. The contractor was given the ability to determine the design, fabrication, and erection of the shell, falsework forms, and pouring procedure, and the decentering procedure. They abdicated the design responsibility for this. Now, other people who designed and then also built shells, by this I mean Nervi, Candela, Torroja, Diesti, all of them knew that the construction process itself was integral with both the design process and the documentation process. And in this, Saarinen's office said, you figure it out. And the odd part was this was a design bid build, which meant that the person who had the lowest bid would be the person who got to figure it out, which meant that the contractor could take risks in how they chose to do this concrete form. And if they got the lowest bid, they could just pick it themselves. George A. Fuller Company was the one who then got the bid and proceeded with the construction. So they decided to build the auditorium first. There's already going to be this tricky shell on top of it, and so they built a raked shell below. So then there's this raked shell, and then they had to almost make a platform on top of it, and with this platform, the next thing they did was they built up the space where the arches would go around the perimeter. While you're looking at these construction drawings, I just want you to think of this. The whole form was 1/8 of a sphere, which is a non-ideal shell geometry. Because it's a non-ideal shell geometry, it means that the shell will probably bend. But they only had 3.5 inches of thickness in the shell, which meant that any bending in that surface of the shell would be dangerous and could lead to failure. Okay, but how would you then define that double curvature shape? You're actually out here building. You're not going to have these magical radius points of section and plan. So what they did was, because this didn't take the form of an efficient shell, Ammann and Whitney said, well, there's probably going to be bending, so why don't we just have that bending go into these arches? So they have 3 arches that they went around the perimeter. These arches, unfortunately, took on more stress than they were planned to. They became the root of all the problems. So then they formed the arches next. You can see the arches being formed around the perimeter here. And then on top of the raked auditorium, they then decided this is when they would define the double curvature of the shell. So the accuracy of these verticals obviously was a problem. They didn't have any real way of being able to measure these things. That's a view to the underside of the auditorium looking up. That's the actual scaffolding. Now imagine how accurate you'd have to get it in order to then pour this so the shell could only have such a thin 3.5 inches of thickness. So they added these contour bands that went around it. These contour bands ideally then were set at one particular elevation so that you could judge and make sure that you're on the right track with the overall geometry. Here you can see it being built. But pouring the shell became a huge problem too, because again, they had let the contractor choose how to pour the shell. This isn't something that you just let somebody pick because there's structural implications with it. So George A. Fuller Company decided that they would pour the shell in 3 separate pours, starting at each of the feet, and then work their way up towards the middle. But this took forever. The shell was poured across 100 days, basically throughout the entire winter. Concrete already has problems in cold weather. And so there's obviously structural issues that could happen with the concrete. And then when you have cold joints being poured in the concrete, joints that weren't planned on in the structure, the shell could have even more problems. Because he didn't design the construction, look at how difficult this gets. It's a double curved surface, huge rebar that's in there. Even the formwork and how the concrete is being laid, look at the integral beam there, how there's some concrete that's sort of in the integral beam, how he's kind of spreading some underneath the beam, but kind of moving it out. What's he even standing on? Look at the screed that he has behind him that he's going to try to move across that surface. So that's a flat 2x that he's just going to kind of move and hope that it makes a double curved. You can see one of those halo boards in the middle here that's defining the kind of edge or thickness of it, then that would be removed. All of this is an incredibly difficult pour, especially for an inexperienced crew. Kresge, when it was done, was over budget, and eventually they knew that they had to fix this construction project. So they didn't want to really celebrate this, and it was sort of a hidden solution. They ended up putting steel columns within this glass curtain wall and justified it by saying, oh yeah, a curtain wall needs a steel column. But those steel columns go up and they support that concrete arch. So when you look at this project, it does look like it's a concrete roof that's floating above the glass. But just know that within that glass wall are steel columns. Those steel columns support the arch because the arch bends too much because it was designed in a way that wasn't structural. And here's Saarinen with sort of the understatement. One has to criticize the building. Now, he says this, it's a loaded statement. What he was actually mad about wasn't its response to construction or even structures. He didn't think it floated enough. He thought it was, he called it landbound. So here's a sketch that Saarinen did shortly after the completion of Kresge then for TWA Terminal. And I love Kevin Roche's quote about it when I interviewed him for this. It was more of a structural problem than a structural solution. So here's Saarinen sketching literally on the back of a menu to show someone what his idea about the TWA terminal would be. Look at the aggressiveness of it. Look at how it's a bird, it's flying, it has motion. But at the same time, I want you to look closely at some of the sketches because you see, like Kresge, he has a functional idea in mind about moving in, entering in, moving around a terminal, and going out. And so the form of this here was also then again about function and expression. But what we don't see here is him thinking any more about construction or the structures. However, Ammann and Whitney were on from the start. So Saarinen, in one of his famous speeches, talked about structural rational. So look at what that quote says. This is dangerous, but I believe true. He's willing then to say that if something is more beautiful, it takes precedent than the rational and structural. And this is what made Saarinen, of course, a celebrated architect and also reviled by people like Nervi, who hated this idea. So given this perspective of Saarinen, Ammann and Whitney tried to figure out how they could learn from Kresge, help Saarinen learn from Kresge, by working collaboratively together. So TWA, this was one of the first models they had of it. All 4 of those bumps were sort of the gates and the entry. And so Auditor, who was a young engineer working for Ammann and Whitney, called it a creature which started off wild. Here's how it evolved. It changed to be 4 separate shells. Each shell could be cast separately, and at each joint there would allow light into the interior. So all of this seems to make sense. Where did this come from? Whose idea was this? Why would this go from this to that? Now, Saarinen, of course, claims that it was too dark inside of that building and he wanted to have skylights. The way to have skylights in there was to actually articulate each one of these separate clover leaves. Auditor suggested that he was the one who told them that each one of those leafs had to be poured as one separate pour. Therefore, they had to be limited in terms of their size. It doesn't actually matter. What matters is the project evolved to the point where a structural and construction idea was actually embraced as an architectural solution as well. So then Saarinen's office had these large-scale models that they did for TWA. How they built the models, and they had these ridged beams. So these beams were sort of, there's no actually beams inside of there, but they define the end geometry of the curves. And that affected how they then documented the project. So instead of Kresge, where they had obscure radii, they actually then would build defining perimeter profiles and start filling those in with like ruled surfaces. So Kevin Roche's quote here again is spot on. It was a 3D idea that needed to be converted to 2D in drawings and then back into 3D when they built it. So Saarinen's office embraced the idea and would just draw how they built the model. So they had 130 architectural and structural drawings, and it was thoroughly documented. Unlike Kresge, they really focused on what it would mean to build it this way. So they did serial sections and even contour elevations like the model. So you can see as you're moving through the serial section how that geometry would change. And you see the points on the side here where you'd be able to look at and decide what the key elevations were. Here's some of the structural drawings that show then the rebar geometry, how it would be cast, where it would be cast. This is an architectural model of one of the support legs. In it, you can see that they would define the outside curving geometry, and then inside of it with a ruled surface for each one of the shells. They would then measure this, they would photograph it, measure it, and use this, as you can see here, to document in their construction drawings. It's a beautiful drawing on its own. You can see this is part of their construction set. Here you see another one that helps define. The other thing that changed with TWA is they had a very highly detailed requirements for construction spelled out. In fact, in their specifications, now Ammann and Whitney and Saarinen, so that it would be a 9-month process for the contractor to develop a plan to pour it. So the contractor had full-time people there on site whose only job for the first 9 months was to figure out how they were going to pour the shell. Saarinen's office had somebody full-time. Ammann and Whitney's office had somebody there full-time. This is an incredible departure from what was found in Kresge. It was also designed a system that made a lot of sense. Unlike the random scaffolding for Kresge, there was a rigorous and regular grid. So there was 1,800 scaffolds. And get this, there was a computer that was on site. This computer was used to determine the correct elevation of each vertical. In here you can see both a plan and then up above a section. So then each scaffolding would come up, there'd be a little receiver up there, then they would be able to take a curved piece between all those receivers to try to define the correct geometry of that curve. So here's the challenge though. To avoid the cracking, each quadrant needed to be continuously poured in only 24 hours. 1 day. 100 days for Kresge, 1 day per quadrant. So they made test forms and they poured the test forms. On top of the forms, they even had these spot elevations. Can you see that? Like plus 42, plus 35, plus 29. So that when you were pouring it, they'd be able to determine about how much concrete would need to happen on those things. Down below, they had different slump levels for each section. There was a mobile concrete batch station on site, and they had 3 different concrete plants on call during those 24 hours in case something happened. They weren't taking any risks at all with this. Contractors were assigned 1 spot during pouring. 150 workers poured each section. They even wore, as you can see here, numbered shirts. And just an incredible feat of engineering and construction. They poured 1 cubic yard every 2 minutes. So you had concrete trucks out there lifting, pouring, lifting, pouring. So inspection crews were down below because they wanted to make sure it wasn't going to sag. And it actually sagged less than 1/4 inch total. No noticeable shrinkage cracks. So of course this is all of a result of actually matching some of the form to the structure and to be thorough about the construction documentation of it. and to have a system in place about how it's built, to start connecting, as the other people worldwide had done, this idea of design, form, construction. Here you can see a quote from the foreman of the job, and I think it's apt, and I absolutely adore this picture of TWA before it was painted. And Ada Huxtable, she has such a great critique of it here, because I do think it's true. A stunning manipulation of reinforced concrete into unconventional forms of arbitrary but dazzling grace. And I'm sure Saarinen would have appreciated that if he would have been alive to have read that. And I think Kevin Roche's quote here is actually true too, and I think it speaks as to why the building is still enduring today and how we see it. Because it's more about an experience than a piece of engineering. So obviously, because Kresge was a problem, it led to some incremental changes then for TWA. Saarinen then started to accept and embrace a greater level of influence by his engineers, particularly Boyd Anderson, who was the project engineer for both Kresge and TWA. During the time that TWA was being designed, documented, and built, Saarinen actually collaborated with a different engineer. This one was Fred Severid, and Fred Severid became a trusted collaborator very quickly and got Saarinen really interested in the idea of tension as a way of being able to define structural form. So Severid, as you can see, Eero Saarinen praising him here about the unique 20th century technology of tension. And then in these sketches that Saarinen did for the hockey rink at Yale, he was able to show how the arches themselves would be supporting, and either to the side or central, but these would be arched concrete. But then the roof itself would have a sag of the tension. And so with that, Saarinen is here trying to express both the function of a hockey rink, wide in the middle, narrow at the ends, more people being able to watch it in the middle of the ice, enter in, exit to the side. He's trying to show you again what he was doing with Kresge, which is plan, and then the section, and then the expression. But in this now, you can see that he's starting to pay attention to the actual form itself as something that's derivative of the structural principles. So, he had finished this up in 1957, the Ingalls hockey rink. And then in 58 through 63, he worked on the Dulles Airport. Now, again, with the Dulles Airport, he went back to working with Ammann and Whitney, particularly Boyd Anderson. And by this point, Boyd Anderson had been a close collaborator with him. And I think that what's so interesting about this quote from Kevin Roche is he said that Saarinen had this scheme figured out right away. Like with TWA, he had an image in mind, and so he had sketched this Parthenon-like sketch in the upper left, and then a whole series of different sections down here on the lower left. But he was saying that with Saarinen, it was hard to separate the structural solution from people movement. So Saarinen had a huge open front porch, and you can see in the model down here, and it was meant to then funnel people down and in to the gate. This was the first sort of jet bridge, which was then a vehicle that was designed to take you out to where your jet was. So it was all about one big room with a giant roof over it. So it was expressing both the time and convenience of how you would enter in and move your way through. So then Saarinen, right before he died, actually talked about the design of Dulles, and you can see he talked about a logical, imaginative, and responsible answer. That hardly sounds like the same person who designed Kresge, right? So what's interesting about these drawings here is you can see on the left, these are then the construction drawings of the giant arms, the ones that are going to be holding the roof structure back. Look at the geometry of the arm itself. Look at how the shell is tied back into it here. Then you see the forces, the rebar that are in there, the giant counterweight of the foot. All of this then is just to show you the thorough documentation of the structure. Nothing is left to chance. The formwork is not to be worked out in the field. Then over here, what you see is what became the ingenious part of this is there were a whole series of arms. I'm going to back up. A whole series of arms that would support this roof. How do you cast a roof like that? Through all the same process that you did with Kresge and TWA with all the scaffolding? No, instead they came up with this ingenious plan where actually between the arms you would hang cables. Remember the influence of Fred Severid and the tension. So they would hang tension cables, and within these tension cables they would put precast slabs. The precast slabs would then slide down. You can see right here on the bottom right. Here you have the cables. Precast slabs are going to move their way down. Eventually, you'll be able to cast all of them together. You can see on the top here. Then eventually you cast it all from the top. So what's happening here isn't just a design of a building form that's responsive to structures. Now the structure itself is super responsive to the building process. Look at what the specifications at Dulles say now. The work herein proposed for development is highly original in character, will require considerable ingenuity and very skilled craft workmanship in its construction for obtaining the form and effect contemplated. Basically, be warned. And look at the craft. So you can also see here they're starting on one side and they're working their way down. So there's this assembly line about this process too, which makes it so super efficient. By the time you're finishing up one arm that's then cured, you can move on to the other. And as those are curing, then you can have another crew that comes back and affixes the top, and then you hang the cables, you put the concrete precast in. Just an absolutely incredible picture of it. This is the underneath side of the shell when it was poured. It held itself. The tension cables were then encased in concrete, and the roof was encased in concrete, and all the precast was unfinished, so it looks like it's all a monolith. So how do we get this way after 10 years? So there's another key evolution here. Saarinen finally was willing to accept and embrace a greater level of influence and expertise from the structural engineers during their early stages. I would also contend, though, that Saarinen was learning. He had never done a shell before Kresge. This was his third shell, and he was a brilliant man. He absolutely understood how to design things, I think, that had just an incredible insight into their aesthetics. And as he learned that both the construction and the structural performance is where those aesthetics lie, he worked his way towards that. So he found this increased level of expertise in concrete shell design, and certainly his team and Ammann Whitney's team invented a much higher level of documentation in both offices. Saarinen died unexpectedly in 1961, and he never even got to see Dulles completed, actually. Kevin Roche told me that he had seen the cables hanging down, and he had written his wife briefly before he died. And you can see the quote here that he thought it might be the best thing I've done. Maybe it'll even explain what I believe about architecture. I find this just a fascinating insight into Saarinen, a person who originally said it may be dangerous but true that the beauty may overtake structural engineering principles, now sees the harmony of them together as something that talks about what he might believe architecture is about. As for Boyd Anderson, he was named one of the greatest structural engineers of our time by the American Society of Civil Engineers, largely unheralded and largely unknown in most civil engineering circles. And Kevin Roche, I think, summarized it pretty well in the interview in 2014. Even if some were appalled by the work, it was incredible. And I think that we can be perhaps not appalled by the work. I think it's very instructive work to see how the idea of design and form can evolve when thinking about engineering and construction, not as something that's limited with possibility, but something that, in fact, lights the way towards new possibilities and things that are creative and beautiful. For your reference, here's a few of my references that I've used in these projects and their research. Additional information about this that you may want to look at if you have any more questions. Appreciate you watching.